Okay, our next talk is going to be by Jacob Laurel. Jacob's going to be telling us about synthesizing precise static analyzers for automatic differentiation. And I did want to mention that Jacob is on the academic job market this year.
Hi, everyone. Can everyone hear me okay? Awesome. All right, so I'm Jacob. I'm a PhD student at UIUC, and this is joint work done in collaboration with Brant, Qian, Gagandeep, Singh, and my advisor, Sasa, Misailovic. So hopefully by the end of this talk, I can convince you why automatic differentiation needs precise, general, and scalable static analyses, and why this is possible using our techniques. Now, what do I mean by automatic differentiation? Well, it's a programming paradigm for computing derivatives of source code useful in a variety of tasks like optimization, graphics, scientific computing, and of course, machine learning. Now, what does automatic differentiation actually look like up close? Well, imagine I have some code that encodes a differentiable function. In this case, it's just the exponential function. Now, because it's differentiable, I can think about having another piece of code that can compute that derivative for me. Now, these derivatives are just computed using the standard rules of calculus. Here I've highlighted the statement that encodes the chain rule computation. This is exactly what frameworks like PyTorch, JAX, and TensorFlow all do for you, so that as the developer, you don't need to worry about remembering your freshman calculus class. So the question we're interested in is, what if we want to statically analyze this code that computes these derivatives? Now, we might do this in order to try to obtain some type of formal guarantees. In fact, formal guarantees might even be helpful for understanding something about the original function which we're differentiating. Now, you may be wondering, why bother doing this? Well, what if I want to know, do the gradients explode in magnitude? Or is a program, such as a neural network, a monotonic function? How sensitive is the program to different inputs? Well, all these questions can be framed as formal properties, but ones which are definable over derivatives. Now, we're going to compute these derivatives using automatic differentiation, of course, and these formal properties will be analyzed using abstract interpretation. It's the combination of these two that is the foundation of our technique, Pasado. Now, a brief recap for those that may be unfamiliar. So imagine I have this piece of source code, and here it's a differentiable program because it performs automatic differentiation to compute a derivative. Now, we're used to starting in some concrete input state, executing the program as normal to obtain a concrete output state. But what if instead of starting in a concrete input state, I were to abstract into what's known as an abstract state, which defines an infinite number of possible states? Then I can propagate that through the program using what's known as abstract interpretation to obtain a final abstract state. Now, of course, this requires abstracting things like the exponential function or this multiplication. I can then concretize back, and now I have an infinite set of reachable output states. Noting that in our case, because we're computing derivatives, this is really an infinite set of derivatives. So, for instance, if we can say that they're all greater than 0, we can now establish a formal guarantee, but one that's not just defined over the derivative computation, but over the original program itself, that the original program must have been a monotonic function. Now, we all know the exponential is monotonic, but this same logic applies to more general functions. So the core idea that I'm trying to illustrate is that a property defined over the derivative code can actually be used to prove a property over the original code, which is called the primal. Now, there's three simple rules that govern almost all of calculus. They're the chain rule, the product rule, and the quotient rule. The beautiful thing is that these rules work in both forward and reverse mode automatic differentiation. It doesn't matter the order in which you compute the derivatives, you still have to compute the same derivatives either way. And we can even see this by looking at the source code for the chain rule in both the forward and the reverse mode case, likewise for the product rule and the quotient rule. We see that even though the order of the derivatives is computed, order of the derivatives is different, that we still see the same fundamental patterns emerge in both forward and reverse mode. Now, we're going to notice that these patterns are quite nonlinear due to these multiplications and divisions in the quotient rule. So we might think as a first step to try to abstract these primitive operations. Just as I mentioned abstracting the exponential function or the multiplication in the previous example, we might try that here. And then try to compose together those abstractions using something like interval arithmetic for like interval addition, for instance. But the problem is such a naive composition actually loses precision. This is because a lot of abstract domains like intervals, zonotopes, or polyhedra are well known to be imprecise in the face of nonlinear operations. So we don't want to give up yet. So we revisit these patterns, and we ask the following questions. Is the whole worth more than the abstract sum of the parts? Now, what do I mean by this question? Can we have a single abstraction for the whole expression all at once? And this is exactly the core idea of our technique Pasado, hence our core contribution. So it might help to illustrate this with a small example. Imagine I have this program, and somewhere in the program I have to compute a sigmoid activation function, which is shown on the right. Well, in the derivative computation, which is what automatic differentiation computes, we see this is the computation I have to perform. I have to do the sigmoid x times 1 minus sigmoid x, which is the derivative of the sigmoid function. Now, in our case, we're trying to abstractly interpret this whole expression all at once. Hence, Pasado abstractly interprets the chain rule. So we might look at this expression, which we're trying to abstractly interpret, this sigmoid of x times 1 minus sigmoid of x times y, and we might note that it's quite nonlinear. We have several multiplications, and the sigmoid itself is a nonlinearity. But by looking at this graph, we see the function looks close to being linear. So what if we were to come up with a linear approximation of it? Now, by itself, the linear approximation is not sound. We can't just replace every operation in our original code with a linear approximation and hope all is well. But what we can do is try to add some formal bounds to this. So if we can obtain these dark orange linear bounds around the linear approximation, then we can make things sound. The trouble is we have to solve for this d here, because this d governs the amount of offset for the bounds. And notice that the bounds are parallel to the plane that linear regression finds. Hence, the shape is actually a zonotope. So the question then becomes, how do we compute this d? And I'll stress that this is the most important question in order to establish the soundness guarantees for our abstract interpreters. Well, this is not so easy because this is actually a challenging non-convex, nonlinear, multivariate constrained optimization problem. But it turns out if we look at the Hessians, or the matrix of all second derivatives, we can actually make this problem a lot more tractable. So the quotient rule, as an example, this is the optimization problem that we have to solve in order to maintain soundness of the abstract interpreter. Now we're going to look at the objective inside that optimization, and we're going to look at the Hessian in particular. And it turns out that the Hessian of this thing, this four-dimensional function, is actually everywhere indefinite. Now, this may not seem particularly useful, but it means that all critical points are saddle points, meaning the optimal value is somewhere along this four-dimensional boundary. And it turns out we can actually repeat this argument for all lower dimensional boundaries as well. Hence, the optimal value is actually on the boundary, thus turning a four-dimensional optimization problem into a handful of 1D optimization problems that are much easier to solve. So while this idea is nice mathematically speaking, how well does it work in practice? Well, take for instance this simple climate model, where each letter corresponds to a physically meaningful parameter, such as heat capacity or temperature. So the actual code that we're going to analyze is this numerical ODE solver. We can see it's just a for loop and some assignment statements. Hence, we can automatically differentiate through this piece of source code. And this will allow us to do a sensitivity analysis. Hence, we can understand how sensitive the numerical solution of this ODE solver is to the different inputs or parameters. Noting that in our case, because we're doing abstract interpretation of automatic differentiation, we can do this automatic differentiation through the solver abstractly for ranges of values. Hence, we can analyze a range of physically meaningful values for these conditions. So here are the results, and what I'll first point out is that these blue dots represent the value of performing the automatic differentiation for individual points without using abstract interpretation. If one were to just sample points in those intervals that I mentioned and just run the automatic differentiation on just those points, you would get these blue dots. And hence, the goal is to try to tightly enclose these blue dots as tight as possible. Now, with interval arithmetic or zonotope arithmetic, both of which are standard numerical abstract domains, when you apply those abstract domains to automatic differentiation, you get the green and orange bounds. Now, Pasado's bounds are those shown in purple, and they're actually the most precise in all cases. We also will mention that the purple bounds of Pasado are always strictly greater than 0. So, for instance, we can prove monotonicity. So, we generalize this idea into a full evaluation whereby we compare Pasado against interval and zonotope autodiff on 4 case studies. And we use the implementations from our previous papers as the baselines. So the next case study was a Lipschitz robustness with respect to adversarial perturbations. So here we take different neural networks, including some convolutional neural networks, which are quite large. And what we want to do is find the smallest k such that it upper bounds the magnitude of the gradient with respect to the amount of perturbation that the adversary can apply, where the adversary can apply any amount of perturbation from 0 all the way up to alpha max. In particular, the perturbation that we're considering is the haze perturbation, where they can apply some haze effects to an image. And this requires using the forward mode for Pasado. So here are the results. And on the x-axis, we have the alpha max, which represents the interval width of the input perturbation that the adversary can apply. And so that's our abstract input state. And on the y-axis, we have the bound on the local Lipschitz constant, and lower is better. So we can immediately see that Pasado, which is shown in green, is the lowest. Now, one thing that I'll mention is that these y-axes are shown on a logarithmic scale. Hence, Pasado is not just slightly more precise, but rather it is orders of magnitude more precise. And when we look at the runtimes, we see an equally interesting story, and that in the first 2 cases, Pasado is not too much slower, so for just a slight increase in runtime, you get orders of magnitude more precision in your bounds. Now, in the last case, Pasado is actually slightly faster than zonotope abstract interpretation of autodiff, and that's because Pasado is also more memory efficient in that it stores less noise symbols overall. I won't get into that, but I'll just mention that due to this memory efficiency of Pasado, in some cases for particularly large benchmarks, that's actually what allows us to be faster. So our last evaluation was a monotonicity analysis of a deep neural network. We take the adult data set, which is a popular data set in algorithmic fairness, and there's multiple categorical features, but we're particularly interested in these continuous input features, things like number of years of work experience, among others. And we want to prove monotonicity with respect to these features, because this monotonicity is an interesting notion of fairness that has recently emerged in the literature. And hence, if we can prove monotonicity with respect to these 5 features, that's our goal, and that can be used as a proxy for fairness. So we have to instantiate Pasado in the reverse mode in this setting, and what I'll mention is that each input represents an individual, and what we do is we put an L infinity ball of radius epsilon around each individual. Hence, we're not just analyzing the qualities of the classifier on a single person, but rather on an infinite range of possible people. And so we want to prove as much monotonicity as possible. And so in this graph, higher is better. And what I'll mention is that Pasado is the highest. The purple line curve of Pasado is higher than both interval and zonotope abstract interpretation of autodiff, again, due to Pasado's improved precision in terms of how it's able to precisely synthesize abstractions. And while the runtimes are a little bit more for Pasado, I will mention that compared to interval abstract interpretation of autodiff, Pasado is able to prove about an order of magnitude more problem instances as monotonic. So there's some more stuff in the paper for those that are interested, such as the full soundness proofs, full experimental evaluation, and our code is available for those that are interested. So just to conclude, I'll say that abstract interpretation of automatic differentiation with Pasado, it's precise because we can synthesize precise abstractions for the chain rule, the product rule, and the quotient rule. It's general, it's scalable, and there's a lot of problems at this intersection of automatic differentiation and programming languages, and if you're interested in more of these, I'm on the academic job market this year, so feel free to reach out. Thank you.
Questions?
Hi, this is really cool. So there are two things I didn't understand. So one is when you find the zonotopes or those approximations that you build, how are you guarantee that they actually are non-trivial, like the curve?
So are you talking about, I can get back to the slide.
Yeah.
The slide?
Yeah, I mean, if you have a weird curve like quadratic, then this can become that the approximation is the entire hyperplane.
So we only look at the chain rule and the quotient rule and the product rule. Those are the only patterns for which we abstract a bound for. So in the general case, for like an arbitrary type of numeric computation, there's not a soundness guarantee for those, but for specifically the computational patterns that are found in automatic differentiation, those are what we do guarantee the soundness for, and that we're able to reduce this down to a handful of one-dimensional optimization problems. And I will, so these 1D optimization problems, this is sound for the differentiable functions for which we consider in our language. So.
Okay, got it. So the last part, I was surprised to not find that your last slide was going to be that you can also do abstract training using this abstract domain. Like, can you do like the same that they do with zonotopes, where now you have an objective and you want to train for that instead of just verifying?
Yeah, so that's a great question. So in terms of can you use this technique for training, absolutely. You could use this verifier that we have inside of a training loop, and you could try to train like a neural network to have small gradient bounds, if that's the question.
But how do you pick the bounds to do the back propagation at the point?
So I guess through this, because you have to solve an optimization problem, so it may not be like this particular method in terms of like getting R bounds may not be, as easy to automatically different, like in terms of using our solver inside of a training loop, it may not be possible, but in the general case, using something simpler, like say interval arithmetic or regular zonotope abstractions, those probably could be put inside of a training loop. But for this is mainly targeted towards more of a post-training verification stage. So
thank you.
Any other questions? Okay, let's thank the speaker again.